Assalamualaikum warahmatullahi wabarakatuh and hello. Okay, today we will continue with chapter 5, which is transformer. Okay, for this class, I'm not sure whether it will have attendance or not, but check the e-learning or check the description because I still cannot set the attendance system. Okay, so we continue with our chapter 5, okay, which is part C, practical transformer. Okay, in the previous learning, you learn about the ideal transformer, which is P input is equal to P output. There is no losses. But the real transformer is not like that. There will be losses. P input will not be equals to P output. So today we will discuss about the losses and how to calculate the practical transformer. So the first losses that you need to consider is the flux leakage. Okay, also called as leakage reactance. Okay, if you can see the figure here, okay, there are, when you do a winding, okay, at the winding you can see that there are leakage fluxes. Okay, not all flux will goes into the the core. Okay, some flux will goes outside the core, and this called a leakage fluxes. Okay, so you have to consider this in the in the circuit, okay, equivalent circuit of the transformer. So if you draw back the ideal circuit, okay, remember the ideal circuit, so you have input, okay, or the primary, can you have the primary winding, and then you have the secondary winding. Okay, so this is ideal, and then you have to include the flux leakage or the leakage reactant. Okay, so what it means that, okay, this is ideal. Okay, so maybe I just use the different pen. Leakage reactance, okay, means that you have to put the inductor, okay, to represent the flux leakage. Okay, represent flux leakage. Okay, and this one is usually called L1 and L2. Okay, that is what is leakage reactant is. Okay, okay, the next thing that you need to consider is the magnetization current and core losses current. Okay, although the output of the transformer is primarily open circuit, there is still a current flow to the primary winding. So you have to refer back to chapter 4. Okay, so basically electrical circuit change to magnetic circuit. So this current is the magnetization current and the core losses current. So the relationship, you have to refer back to chapter 4. F equal to Ni equal to S flux and I equal to S flux over N. Okay. Okay, this current, okay, the current that you see that is this from the eddy current losses, okay, it is depend on the rate of change of flux and the hysteresis loss, a non-linear loss. So this one you can refer back to chapter 4 to see why this happened. Okay, basically at no load, the primary winding is known as the primary winding is known as the excitation current. So I will show you in the next slide. So before this, you see that there are magnetization current and the core losses. Okay, and this is the excitation current. Okay, so how to draw this in the circuit? Okay, equivalent circuit. So basically, you have to add a new, okay, excitation current, okay, I flux, oh no, this one is equals to magnetization current, okay, I m n, not n but plus the core losses current I c. So from this one, you have to draw a this one divide into two circuit. Okay, so you have these two. So this one is RC, core losses, and this one is magnetization reactance. Okay, XM. And the current goes here is the IM. The current goes here is IC, and this one is the excitation current I flux. Okay, that is the component that you need to consider in the practical transformer. So you have R and inductor and resistor. And then, okay, this is just a theory. Okay, that you need it doesn't too much important, but it's just need to know basis. Okay, you can see that this in theory that flux produced in the core is sinusoidal. Okay, and the current also produced sinusoidal, but this is not true. Okay, basically, if you apply sinusoidal current, okay, and the flux will not be sinusoidal. Okay, it will not produce a sinusoidal. So basically, it is combination of sinusoidal and high frequency oscillation, and the current lag voltage at 90 degree. And when the saturation occur, the high frequency component will be very extreme. So this is just a theory. You don't need to focus too much. So right now you already look at the eddy current and hysteresis losses, the leakage flux, which is the X1 and X2. Eddy current and hysteresis losses is RC and XM. Okay, now the last thing that losses occur is the copper losses. This one is basically the losses caused by the winding. Okay, you can see that there are a lot of winding. So this one can be represented as the resistance. Remember that I said that in wire they are resistant, even though it is very small, but it's still considered, because in winding there are thousands of number of turns. So the resistance will accumulate and become quite large. So you have to also consider the copper losses, okay, at the winding. So how to represent these copper losses is basically you add a resistor. Okay, this one also resistant. So this is R1, this is R2. Okay, so you represent this R1 and R2. Okay, and then, oh, before I forget, okay, this one is usually we represent as, okay, better standardize it. Okay, this one is JX1, JXL1, JXL2. Okay, this one is JXLN. So basically this is the ideal transformer equivalent circuit. So you have the leakage reactance, okay, which is, okay, this is the copper losses. Okay, if you look at the green, it is a leakage reactance. If you look at the blue, it is excitation current. Okay, the magnetic current and the core losses current caused by the eddy current. Okay, then and the hysteresis loss, and also, and lastly, you look at the red one, it is the copper losses at the winding. So you have all these losses and you represent it, okay, represent this in the circuit here. Okay, so make sure you know how to draw this. This is important circuit. So what we can conclude is that, okay, there are three things that you need to consider in practical transformer. So make sure you know the difference between the ideal and practical transformer. It's basically, in ideal transformer, you neglect the reactance, leakage reactance, but in practical transformer, you include the leakage reactance. And for ideal transformer, you also don't include the magnetization reactance and core losses. But in practical transformer, you include this parameter. And lastly, for ideal transformer, you don't consider the core losses, but the ideal practical transformer, you consider the copper losses. Okay, make sure that you know the difference, because this is quite important things that need to be considered. Okay, when it comes to practical transformer. So make sure that you memorize everything. Okay, this is the equivalent circuit of a practical transformer. As I mentioned before, this is the derivation. So you have RP, JX1, or this case you use primary and secondary. Okay, either you can use 1 and 2 or primary and secondary. Both are correct. And you have the RC, XM, okay, RC, R secondary or R2, JX secondary or JX2, and lastly is the load. Okay, make sure do you know the difference between the V and E. Okay, E is the ideal transformer at the center, and V is the at the terminal. Okay, at the left hand side and the right hand side. Okay. Okay, so remember that from the previous, okay, ideal transformer, you know that, okay, we use back the ideal transformer. A, or turn ratio, equals to N1 divided by N2 equals to E1 divided by E2 equals to I2 divided by I1 equals to square root of Z1 divided by Z2. So remember this back. Okay, make sure you know how to get this first. Okay, the turn ratio, and then you can do all of this. Okay, so basically we have, normally we move every refer to primary. So usually we refer to primary. So basically means that everything in the secondary part we bring to the primary part. So you have this one, V1, okay, and then you have I1, okay, you have the resistance, okay, R1, okay, the copper losses, and then the leakage reactance, JX1, okay. So remember back, X is equal to WL, okay. So you need to remember back what is reactance. This is reactance X, and what is mean, okay. So then you have the, okay, the core losses, which is RC, and then the magnetization reactance XM, JXM, okay, and then lastly goes here. So now in ideal, you remember that we have to eliminate this, and we have to bring all of these to the primary side. Okay, how to do this? Okay, just copy back. So this one, okay, you have R2, but instead of just R2, you have to put the A, the turn ratio. Okay, and then, and don't forget A squared, because this is, remember this one, there is a square root, and then if you bring here, it will become square. Okay, so you need to know for reactance, okay, you have to put square. Okay, and then you have any inductance Jx2. Okay, and also don't forget to put a squared. Okay, make sure every time you involve impedance, any value of R, XL, L, C, okay, make sure you square the A. And this one, okay, this one is V2, this one is, okay, E already eliminated. This is E. Okay, you already eliminate this. No need more. Okay, and this is V1, this is V2. Okay, so basically we want to eliminate the transformer. And then this is I2. Okay, and then don't forget the load. This is ZL. Okay, and because we bring to the primary side, also don't forget the A squared. Okay, don't forget the square. A squared. So basically this is the refer to primary for ideal transformer. Okay, now you already get the refer to primary side circuit. So but the problem is it is hard to calculate. You can see that there are a parallel circuit in the center of the circuit. So basically what you have to do is you do approximation to the equivalent circuit. So how to do that is basically by moving the RC and XM to the left side. Okay, you basically move to the terminal. As a result, you can obtain a simpler circuit that can be calculated easily. So basically just this is called this one is a equivalent circuit. Okay, this is the equivalent circuit, and then you have to simplify it or approximate equivalent. Okay, so basically you want to simplify this circuit because this circuit is quite difficult to calculate. So you have a series, you have a parallel, and it is not in the easy position to calculate. So what you have to do is you just move this thing into here. So the approximate circuit is become this. Okay, if you have something like this one is or positive negative is V in. You have this one. Okay, you have the one inductance here. JXM RC, and then you have this one and this one. So you have R1, R2, this one is JX1, okay, don't forget S squared, this one A squared, JX2. Okay, so basically you have a simpler circuit. So you have more simple circuit right now. Okay, you can say that easier to draw something like this. V1, okay, don't forget this is V2. Okay, you have this one winding, resistance, this RC, J, XM, and then you have a resistor here. Because this is in series, you can combine together. Okay, and then you have a inductance. Okay, you can combine together here. This is the same component. So this one. Okay, this one is A squared ZL equals to Z L bar. Okay, and this one is Z equivalent. Usually it's called ZEQ. Oh, sorry. REQ and X JXEQ is equals to x1 plus a squared x2. This one is r1 plus a squared r2. Okay, so you have a small, this one is a approximate or simplified equivalent circuit. So when you do calculation, we usually use this circuit because it is much more easy to calculate. Okay, now you can see that the approximate or simplified equivalent circuit refer to the primary side and the refer to the secondary side. Okay, the previous figure I show you mostly on the refer to the primary side. Okay, you also need to know how to refer to the secondary side. Okay, and it is important to you for you to know how to draw and label everything properly. Okay, make sure you know how to label everything. Make sure where is the A. Okay, where is the current. Okay, if you look here, okay, make sure that you know everything. Okay, so remember that from the previous, okay, ideal transformer, you know that, okay, we use back the ideal transformer. A or turn ratio equals to N1 divided by N2 equals to E1 divided by E2 equals to I2 divided by I1 equals to square root of Z1 divided by Z2. So remember this back. Okay, make sure you know how to get this first. Okay, the turn ratio, and then you can do all of this. Okay, so basically we have, normally we move every refer to primary. So usually we refer to primary. So basically it means that everything in the secondary part we bring to the primary part. So you have this one V1, okay, and then you have I1, okay, you have the resistance, okay, R1, okay, the copper losses, and then the leakage reactance JX1, okay. So remember back, X is equal to WL, okay. So you need to remember back what is reactance. This is reactance X, and what is mean, okay. So then you have the, okay, the core losses, which is RC, and then the magnetization reactance XM, JXM, okay, and then lastly goes here. So now in ideal, you remember that we have to eliminate this, and we have to bring all of these to the primary side. Okay, how to do this? Okay, just copy back. So this one, okay, you have R2, but instead of just R2, you have to put the A, the turn ratio. Okay, and then, and don't forget A squared, because this is, remember this one, there is a square root, and then if you bring here, will become square. Okay, so you need to know for reactance, okay, you have to put square. Okay, and then you have in, okay, any okay, inductance JX2, okay, and also don't forget to put A squared. Okay, make sure every time you involve impedance, any value of R, XL, L, C, okay, make sure you square the A. And this one. Okay, this one is V2, this one is, okay, E already eliminated. This is E. Okay, you already eliminate this, no need more. Okay, and this is V1, this is V2. Okay, so basically we want to eliminate the transformer, and then this is I2. Okay, and then don't forget the load. This is ZL. Okay, and because we bring to the primary side, also don't forget the A squared. Okay, don't forget the square. A squared. So basically this is the refer to primary for ideal transformer. Okay, I already show you how to do the approximate or simplified transformer equivalent circuit. Okay, now you need to know the justification. Okay, you need to know why we can move it to the left side. Okay, in reality, okay, if you have the circuit in the center, you cannot just move it around. Okay, the answer will be different. But for this case, you can do that. And the reason is, okay, the reason is why the approximate is acceptable, because the R1 and JX1 is significantly smaller compared to RC and JXM. So the voltage drop across the R1 and X1 can be neglected. So RC and JXM can be moving closer to the power supply. Okay, so this is the justification you need to know. Okay, try to memorize it. Okay, some question doesn't consider the excitation current, so you can neglect the R, okay, the RC and XM. Okay, you just remove it. Just take the copper losses and the leakage reactance. So your calculation will be much more simpler. So how to choose the model correctly? Okay, if you the question do not give any excitation current, RC or XM, use this model. Okay, if they don't mention the excitation current, RC or XM, okay, just ignore it. Okay, if the question said that use approximate model, okay, and if they said that use the approximate model, use the previous one. Okay, make sure that you know which model is to use. Okay, as I mentioned before, it is very important to know how to draw, okay, approximate or simplified, okay, equivalent circuit. Okay, refer to primary and refer to secondary. Okay, make sure you know how to draw this. Okay, okay, not only draw but label it properly. Okay, if you cannot draw this properly, you cannot answer many of the question. So first thing, you have to label it. Okay, refer to primary. So V1, okay, and then this is I1, okay, I1 or I primary. So when you refer to primary, don't forget, okay, this one, and okay, this one is RC, this one is JXSM, okay, and then you have a resistance, inductance, okay, okay, this one is load, okay, this one A squared ZL, okay, and then this one is Req equals to R1 plus A squared R2. This one is JX, okay, JXEQ equals to JX1 plus a squared jx2. Okay, so make sure you label this. So this one is I2 divided by a. Okay, so I2 divided by a, and okay, make sure you remember this, I2 divided by a. Okay, and then this one is IC, this one is IM, this one is I flux. Okay, you have to label it and make sure you know what is all of this. So V1 is primary voltage, V2 is, okay, don't forget V2, this one is V2. Okay, V2 is the secondary voltage, I1 is the primary current, I2 is the secondary current. Okay, A is the turn ratio. What else? So R1 is the copper loss resistance. Okay, R2, this one is primary, this one is same thing, secondary. X1 is the leakage reactance. At primary, and X2 is the leakage reactance at secondary. Okay, what else? Okay, RC is the core resistance, core loss resistance. XM is the magnetization losses, magnetization reactance. Okay, magnetization reactance. Okay, so what else? What is IC? Core losses current. IM also, you need to know what is IM, magnetization current. Then I flux is the excitation current. So you have to know how to draw one and how to label everything properly, and make sure you know whether to multiply or divide. Okay, if you refer to the primary for the impedance, okay, make sure you multiply the A squared, but for the current you divide by A. Okay, so V2, and don't forget V2A. Okay, V2A. Okay, when you bring to the primary side, V2 become A V2, but for current is divided by A. Okay, for this one is multiplied by A and then squared. How about refer to secondary? You also need to know how to draw the refer to secondary. So V1. But when you refer to secondary, make sure you divide by A. Okay. Okay, if refer to primary, V2 bring to V1, and don't forget to bring multiply by A. But if you bring V1 to V2, okay, you have to divide by A. Okay. For the primary, remember, for the primary things, you doesn't change anything. Okay. But if you refer to secondary, the primary will be changed. Okay, and then resistance, inductance. Okay, so this one is RC divided by A squared. Okay, so if we refer to primary, you multiply by A, now you divide by A. And then this one is I1 divided by A. Okay, I1 divided by A. Okay, for current is divide. Oh, sorry. For current is multiply. I1 A. Okay. Make sure you know the difference. So this one is JXM divided by A squared. Okay. And then you have resistance, you have inductance for the, okay, and then, okay. So this one is just leave it like that, just ZL, because this is the secondary side. So Req is basically R1 divided by A squared. Okay, previously we left the R1 because it is in the primary side. But for this time, you have to divide by A squared. A squared. So A squared divided by A squared. And then plus R2. So R2 leave it like that. For JXEQ equals to JX1 divided by A squared and plus JX2. So this is I2. Okay, this one is V2 and then this one. Okay. So make sure you know how to draw both of these. Know how to draw both of these. Label the location of A properly, and then know all of this. Okay. You need to know all the legend. Okay. You have to memorize everything, and then you have to write it. Okay. Make sure you know how to do this. Okay. Be careful, eh. So where the A should be? So this one is divide. Okay, this one is left out. Okay. Okay, next parameter that you need to know is the voltage regulation. Okay, basically at no load, okay, your voltage will be high. But when you connect to a load, the voltage will be reduced. So basically we want a transformer that doesn't change the voltage. So basically voltage regulation is equals to 0. But in reality, it cannot be happen. Okay, there will be voltage drop when you connect the transformer to the load. So you have to calculate the voltage regulation. So you need to memorize this formula. The formula will not be given in the final. So basically V no load minus V full load divided by voltage at no load multiplied by 100. You get the voltage regulation. So the answer will be in the percentage. And of course you need to know what is the efficiency. Okay, efficiency, of course, P out divided by P in multiplied by 100. It is the standard efficiency formula. But also you need to know that P in is actually basically equals to P out plus P core losses plus B copper losses. So sometimes they give the copper losses and they give the core losses, and you have to find the P out. Then you can find the efficiency. So I will show you in the example later how to use all of this efficiency, okay, what type of model use, and the voltage regulation. Okay, this is all for this class. Okay, we will continue with chapter 5C2, okay, which is the example problem for practical transformer. Okay, end of class.